All right, welcome back. So last time we totally nailed strings, right? The published books of Python, unchangeable, locked in. Well, today we're putting that book back on the shelf and we're heading over to the workbench. We're about to get our hands on the single most versatile tool for data that needs to change, add, and grow, the Python list.
Okay, here's our game plan. First, we're going to start with a huge mindset shift, moving from those static books to dynamic binders. Then, we'll get our hands dirty and build a real task manager to see lists in the wild. After that, and this is important, we're heading into the danger zone to talk about a trap that gets, almost everybody. We'll finish up with a live debugging session and then unlock a genuine programming superpower. You ready for this? Let's go.
All right, so think about it. We've been using strings, and they are awesome for text that doesn't change, like a person's name or a title. But what about when the data is alive? What if you're building a shopping cart or tracking scores in a video game? That stuff has to change constantly. And this right here is the big idea. If a string is a published book, once it's printed, it's done. It's immutable. Then a list is a loose leaf binder. It's mutable. You can literally pop open the rings, slide a new page in, pull an old one out, scribble on an existing page. The binder itself is still the same binder, but what's inside can change whenever you want. That flexibility? That is what makes lists the workhorse of Python. Okay, hold on. I get the binder thing, it makes sense. But I'm kind of stuck on the why. Last time, when we wanted to change a string, we just made a new one. It worked. Why can't we just keep doing that? That is the perfect question to ask right now. And the answer is one word: efficiency. Look, if you're just changing one word, sure, making a new string is no big deal. But imagine you have a to-do list with, say, 100 items. If the user adds one more thing, are you really going to make the computer build an entirely new giant string in memory that's 99% the same as the old one? That's like reprinting a 1,000-page novel just to fix one typo. It's unbelievably wasteful. We need something that's actually designed to be changed. We need the binder.
So, enough talk. Let's see this binder in action. What better way than to build something real? We're going to make a simple task manager right here. This is the absolute classic reason to use a list. We need to grab a bunch of items from a user, but we have no idea how many they're going to give us.
Okay, here's the final code we're aiming for. Now don't try to swallow this whole, just look at it as the finished product on the box. We're going to assemble this thing piece by piece, starting with the single most important line. Every collection has to start somewhere, and this is it. This one line, tasks equals empty list. This is so fundamental. It's called the accumulator pattern. What we're doing is creating a brand new, totally empty list. In our analogy, we've just put an empty binder on the table. The rings are open, and it's just waiting for us to add pages. Okay, so I see inside the loop we've got this .append method. What's that actually doing? Great question. Append is how we fill our binder. When Python hits the line tasks.append entry, I want you to literally picture this happening in memory. Python finds our binder, tasks. It opens up the rings, it takes the new page, that entry string, and slides it into the very back, and then clicks the rings shut. That's it. It modified the binder directly. It didn't make a new one, it just added to the one we already had.
And why are we using a loop? Well, think about it. We have no earthly idea how many tasks the user is going to type in. Could be 1, could be 50. So the loop just says, hey, just keep asking for input and appending it to our binder over and over until you see the magic word done. This is exactly why dynamic structures like lists are so essential.
So adding pages makes sense. But what if we finish a task? How do we take a page out? Exactly. This mutability goes both ways. In our code, we could use a method called pop to remove an item. So if we wrote tasks.pop0, that's literally us reaching into our binder, grabbing the very first page, and pulling it out. The list gets shorter, but it's still the exact same binder.
Okay, so we've built our task manager. This power to directly change data, it feels amazing, right? But, and this is a big but, this incredible flexibility comes with a super sneaky trap. It's a landmine that can silently wreck your code and leave you scratching your head for hours. Let's step very carefully into the danger zone.
So check this out. I'm going to set up a little experiment. First, I create list_a. That's our binder. It's got 2 pages.
Got it.
Then I write this line, list_b equals list_a. So what just happened? Oh, that's easy. You just made a copy. It's like you photocopied the binder. Now there are 2 of them, list A and list B, totally separate. So if you mess with list B, list A is going to be completely fine.
And that totally logical thought is the trap.
This is maybe one of the most important things to understand about how Python handles lists. List B equals list A does not make a copy. It doesn't create a second binder at all. All it does is create a second name tag, a second label that points to the exact same binder in memory. The best way to think of it is this. We don't have two binders. We have one binder, and now two people have a key to it.
So when we run that next line, list B 0 equals RIP, and then go back to check on our original list A, this is what we see.
Whoa, no way. The original one changed too.
Exactly. This is the moment every single Python programmer has. It's because there was never a second binder. When you used your key, list B, to mess with the first page, you were changing the one and only binder that exists in memory. My key, list A, now just points to that same messed up binder. This is called aliasing, and if you don't see it coming, it will drive you crazy.
So how do we fix this? How do we actually make a photocopy? How do we clone the binder? Thankfully, the solution is super simple. You just use the slice operator, a colon inside square brackets, colon, square brackets. This little piece of syntax tells Python, hey, I don't want another key to the old thing. I want you to build me a brand new, totally separate binder and copy all the pages over. Now, anything you do to safe copy is safe. The original is untouched.
Okay, let's switch gears. It's time for a live debugging session. We're going to look at what is probably the #1 most common error that beginners hit when they start working with lists. So let's say you've just written this piece of code.
Yep, here's my code. Super simple. I made a list, my list with 3 fruits in it. Apple, banana, cherry. Okay, 3 items. So I want to get the third one. Logically, I write print my list in 3. Makes perfect sense. But it crashes every time.
It absolutely does. And when it crashes, you get this very specific, very helpful error message. Index error, list index out of range. Now, that message is your best friend once you learn how to speak its language. Okay, so let's break it down with our analogy. If the list is our binder and the pages are the items, what does it mean to ask for an index that is out of range?
It sounds like I'm asking for a page number that doesn't exist. Like if my binder only has 3 pages and I'm asking for page number 4.
Exactly! You nailed it! But the question is, why doesn't page number 3 exist? There are 3 items.
And that brings us to the classic off by 1 error. This is caused by a core rule in Python and a ton of other languages. Computers don't start counting from 1 like we do. They start counting from 0. This is called zero-based indexing. So in a list with 3 items, the valid page numbers, the indices, are 0, 1, and 2. Asking for index 3 is asking for the 4th item, which, just like you said, doesn't exist.
Just look at this side by side. When we see the first thing, our human brain says item 1. Python's brain sees index 0. Our item 2 is Python's index 1. Our item 3 is Python's index 2. Once this clicks, you'll see index error way less. Just remember, the last valid index is always the length of your list minus 1.
All right, we've covered the basics. We've navigated the danger zones. We've squashed some bugs. For our grand finale, I want to show you something that is so simple and so powerful, it honestly feels like a superpower the first time you use it. It lets us give our programs a memory.
Imagine we're the bouncers at a club. We need a list to keep track of who's already come in so nobody can sneak in twice. Check out this code. We start with an empty list for our entered guests. We loop through a line of people trying to get in, and the absolute magic happens right there in that if statement.
Whoa, wait. If name in entered guests? That's it. It just reads like a normal sentence. Isn't it beautiful? That's the in keyword, and it is your new superpower. It's a Boolean operator that just asks a simple question. Hey, is this name anywhere inside that list? It checks the whole thing for you and returns true or false. All that hard work of checking for duplicates is handled by that one simple, clean word.
But think about what this really means. This is so much bigger than just clean code. Using an accumulator list like entered guests, combined with the in keyword, is how we give our program a memory. That list isn't just data anymore. It's a history. It's a record of what has happened before. And now our code can look at that history and make smart decisions. This is a huge leap forward. So, we've made the journey from the static, unchangeable book of strings to the dynamic, living,
editable binder of lists. We know how to add pages, how to remove them, how to dodge that really dangerous aliasing trap, and how to debug those off-by-one errors. But most importantly, we've unlocked the ability to give our programs a memory. So the only question left is, now that you have this power, what's the first thing you're going to build?